All right. I think we can get started now. So welcome everyone to our iQuiz seminar. This is our first one with the new webinar version of Zoom. So we're working out the kinks. I think everything is okay. But for asking questions, I think you can either put them in the Q&A or in the chat. We'll see which one works better. And Wolfgang has said that he's happy to be interrupted with questions throughout his talk. So before I introduce Wolfgang, next week we have Peter Shore, same time, same place. So that should be really good. So everyone think about coming to that. But today, very exciting, we have Wolfgang Pfaff, our own Wolfgang Pfaff of the physics department here at Illinois, who's new this fall. Wolfgang did his PhD at Delft and then a postdoc at Yale. And then he spent a few years at Microsoft, again in Delft, before joining us this fall. And now he's going to tell us today about distributing quantum information in superconducting circuits. So take it away, Wolfgang.
Thank you very much, Elizabeth. Yeah, it's a pleasure to finally give this seminar. We were originally scheduled in the summer and then it got moved around due to various reasons. Yeah, but I'm happy it can finally happen. So yeah, this is, so I don't have much to report in terms of ongoing work. As Elizabeth mentioned, I've just joined the department. Ongoing work looks very much like this currently. This is a snapshot of the iQuest testbed lab as of last week. And of course, as you can see, we're working hard on getting finally some really new exciting science going there. But since this is still very much work in progress, what I'm going to be doing today is I'll talk a little bit about, well, sort of what you call the state of the art in one of the fields that I'm really interested in. And yeah, that's also experiments that are also going to be happening in exactly this lab that you're going to be seeing here under iQuest. So let's see. So what is, yeah, so the overarching theme of what I will be talking about is the problem of how to smartly and interestingly connect qubits or similar types of quantum systems together. Right, so the goal that we have, of course, is especially in superconducting circuits, is to make bigger and better bottom-up engineered quantum systems, if you like, with the goal of creating things like quantum computers, quantum simulators, or investigating all sorts of kind of interesting physics in these systems. And the question, one of the questions that I'm particularly interested in is figuring out what are, say, interesting or useful ways of making these individual qubits or other components in this talk to each other. Like how can we connect them to each other? How can we perform gate operations between them? And what could the limits be of the types of connections that we can make actually in the lab? So a few things that we can think of that we actually eventually want to have from our connections between the quantum systems, right? So a very obvious one, of course, is we want to be able to make quantum operations between individual qubits with very high fidelity. This is, a lot of people are obviously working very hard on this. But there's some few other things. One that's quite important actually is the degree of connectivity you can reach. For example, ideally you would want full connectivity. So basically pairwise all-to-all couplings between all of your qubits. Obviously, that means certain types of quantum simulations might become more directly implementable. And it's also been shown, which is maybe quite intuitive, that it can lower the acceptable error rates if you want to think of fault tolerance and quantum error correction in the long run. From an experimentalist point of view, there's even more things that are very desirable in this. One aspect is that you want to have these connections very modular, right? That you want to kind of be able to in situ reconfigure your connections or be able to seamlessly attach more and more qubits to your system. And this is, experimentally speaking, it's very important, for example, that you can debug or replace individual elements in a larger quantum system. And finally, something that's that might be interesting is to think about what I would call maybe compatibility, right? That not all of these elements that we want to interface with each other have to be of the same kind, right? There might be different flavors of everything happening there. Right. So, for instance, what I show here, this is a snapshot of a quantum state encoded in an oscillator. Right. So we might not only have qubits, we might also have qubits talk to oscillators, things like that, or completely different kinds of degrees of freedom. You can also think of other things like in a controlled way, connecting open systems to your bigger system to study noise or or quantum behavior in open quantum systems more generally. So there's a relatively big wish list, and yeah, we want to see how we can tick these individual boxes there, basically. So with that in mind, this is basically what I wanna go over today. So I'm gonna start by reviewing a little bit of what are coupling schemes in superconducting circuits, in particular circuit QED-based ones, and what do people currently do to make, for instance, high-fidelity entanglement gates. Then I'm gonna tell you a little bit about how we can use what I would call drive-induced Hamiltonian engineering to enable new kinds of connections between different qubits, and how we could use that to make, say, routable interactions that could basically give us full connectivity in superconducting circuits. I'm also going to talk a little bit how we can use the same tools to make very flexible interactions based on propagating photons by controlling emission and absorption of individual artificial atoms, if you like, and with telling a little bit about how we can use these ideas maybe to implement, say, routing or quantum state stabilizations in open quantum systems. All right, let's start with the first one. How are most people, or how are a lot of people in circuit QED currently work on implementing gate operations between their qubits to start with? So at a very fundamental level, if you like, the physical interactions in circuits is, of course, how electromagnetic modes interact when the fields of the individual modes overlap, right? This is kind of how they interact, is how they hybridize. And you can, of course, have, like, I displayed this in this cartoon. It could be superconducting qubits. So this could be transmons, for example. Of course, you have electric fields and transmission lines. This is how we couple to resonators. And yeah, their fields overlap, and this is how we create interactions. And these interactions become nonlinear because there's Josephson junctions in here, and these systems that basically mix all these fields together. Right? And what you can maybe already tell from this is that the connectivity we can achieve with that is very much set by geometry, of course, right? Because these fields are typically localized in some way. So and this is how we get to how some of the most advanced experiments that we have in this field currently, how they actually look like on the chip. So I'm showing here two examples of some of the very impressive efforts that are being made by IBM and Google, for example. So this is how the qubits in a current IBM chip, the Falcon, talk to each other, right? It's this, this is a geometry that's optimized, I think, for a Bacon Shor code. And here we have the Google version. This is basically this grid. This is inspired by what you would need to do in order to realize a surface code, for example. And you see it's very much dominated by interactions between neighboring qubits to some degree, right? Because this is, of course, how fields overlap. And these layouts that people come up with to make these chips is typically basically it's a compromise between the fidelity that you need and the particular experiment that you want to do that demands a certain kind of connectivity. So this is basically how these layouts are designed. So let's, with that said, let's look maybe a bit of how that actually realizes, how we can actually use these interactions then to realize qubit-qubit gates. And so in circuit QED, we have these hybridization of electromagnetic modes, and there's Josephson junctions in there. And typically what that gives us is different kinds of ways to look at the Hamiltonian, right? So the most fundamental way of how we look at this is this resonant hybridization, to the fact that there's Josephson junctions in the system that mix these fields together. We typically end up with this kind of hybridization Hamiltonian. In case of qubits coupled to resonators, it's what we call the James-Cummings Hamiltonian. Right, and here, so in an energy scheme, in an energy diagram, right, what we see is basically that the states with one excitation in the system are now split by an amount that's given by this coupling constant. When we move from this resonant regime to a detuned regime, right, then we end up with this kind of Hamiltonian. This is kind of, in qubit language, a ZZ type of interaction, where what we now have is that the transition frequencies for the individual qubits now depend on the state of the other qubit. Right, so you see this here, for instance, the left qubit, which I've drawn in red here, is basically has a one transition frequency if the other qubit's in the ground state, and a slightly changed transition frequency if the other qubit's in the excited state. And vice versa, of course. Right, so in the way you can realize these interactions, so there's different ways of how you can couple superconducting qubits together to give you these interactions. Right, one of them is basically, as shown on the lower side, on the lower right here, right, is basically by just having capacitive couplings, for instance, between your different kinds of qubits, right? So you place them very close to each other, naturally meaning that their electromagnetic fields overlap. Or you can also do this a little bit more flexibly in a more by, for instance, using what's called a quantum bus. So you can have qubits that are separated in space, and you use transmission line resonators to mediate the interactions with them due to their oscillating field, respectively. So, and this is yeah, and using this kind of like static interaction between the different modes, it makes it actually relatively straightforward to implement gate operations between these systems. The simplest way you can think about this is by tuning the frequency of your qubits, right? Because basically, if we can start here, say I've made the two qubits the same frequency, then we see that their modes are hybridized. Right? But if I change the frequency of one of them away from the other, then what we get is basically this decreasing ZZ type of interaction, right? Where now the frequency of the two qubits depends, as I mentioned, on the state of the other one. And by changing the detuning between the two qubits, which I can do by changing the frequencies, we can basically modify the conditional dynamics of these two systems. And this is what we can do to implement two qubit gate operations. So what's a bit challenging, and this is, yeah, this is an ongoing, let's say, engineering challenge in the whole field, is basically how do you manage these always on interactions? So this has made it in the past like very difficult to realize two qubit gates of very high fidelity. Of course, people have thought about this for a long time now, and one of the really interesting routes, I think, that people have pursued over the last few years is finding more and more clever ways of how to modulate these interactions, essentially, and use those to turn them on and off very efficiently. So just to give you a flavor of how that works, so you don't just live with this conditional dynamics and tune the frequencies around of your qubits, right? You can do some slightly more interesting things. For example, so this is the cross-resonance gate by IBM. So you have this static CZ interaction between the two different qubits, but what we do, we introduce a drive to the system. So in this case, what they figured out is you can drive one of the qubit at the frequency of the other qubit. And what that basically does is you convert the static ZZ interaction, right, into a controlled rotation on one of the qubits. Right? And so it turns out that if you modulate the interaction that way, you can get a lot more precision in the system and much less crosstalk across your chip. So this is one way of how you can do this. Another example. This is something from Lincoln Labs that's also used in the current Google chips. For example, is you don't couple qubits directly to each other, but you use intermediate qubits as tunable couplers. So what you get there is basically you get now interference between different coupling paths. So you have one qubit, for instance, on the left that's coupling to the other qubit on the right, but you have this other, this tunable coupler qubit in the middle that also couples to both of them. And it turns out that if you modulate, so by changing the frequency now of your tunable coupler in a particular way, that allows you to modulate or to fine-tune some of these couplings very efficiently, and has allowed to make very precisely controllable swap interactions in this system. So this is only two, again, this is only two examples. There's a whole host of other groups that have published very similar results in the last few years that are working on very similar ideas. And as a result, the whole field is now at a state where I would say that a lot of people have reported 2-qubit gate fidelities that have exceeded 99%. For this, which is very encouraging and has enabled a lot of really interesting experiments, for instance, reaching very large numbers for the quantum volume at IBM or realizing the so-called quantum supremacy experiment at Google last year. So again, so the take-home message is here that by modulating interactions and not just living with their static form, we are able to fine-tune things to enable interactions that we can control very precisely. And the question that I'm interested in is basically saying, well, can we do that for more than just nearest neighbor 2-qubit gates, but can we do something more flexible? So attacking basically this problem of how can we reach larger connectivity, or how can we interface things with each other that normally don't like talking to each other, rather than just things that already hybridize to some way. So, and the route we're going to be taking for that is taking a closer look at what happens to our Hamiltonian when we start playing with drives and realizing what kind of interactions we can enable if we do that. So for that, let's first take a little step back and think about what quantum circuits actually look like on the chip, right? Before we even talk about qubits. So we have, to some extent, like everything we have on a chip are basically harmonic oscillators made out of pieces of metal, right? And somewhere on the chip, there's also Josephson junctions that could serve the purpose of superconducting qubits. But at the end of the day, what's important to see is that, so there are these Josephson junctions, but all of the different modes that we see here, so I have here A, B, and C, still to some extent contribute to the field that the Josephson junctions see, right? So at the end, they're coupled here in this example through these little capacitors here. And everything, all of the modes that couple to the Josephson junction are, of course, coupled together by the Josephson junction, because the Josephson junction has the well-known cosine potential, right? So we have the field operators of all of these modes go in the argument of this cosine. And well, the degree to which they participate depends, of course, on what we're doing here in between them. And so typically, this is relatively, these prefactors here are relatively weak for most of the systems that I want to talk about. So what that means, however, is of course that we don't only have these typical qubit-qubit interactions in our system, but we have all sorts of interactions happening in the system, right? Okay, the one that I've shown you, of course, the typical ZZ interaction pops right out of this cosine. If I were to look at expanding it, for instance, to fourth order, you see immediately terms like this coming out of this. And this is the one we've been talking about so far, just in a slightly different representation here. But of course, we can also see that there's a lot of other stuff going on, but they're typically ignored. Like, for example, you can think of swap interactions between qubits. And if these modes that I'm considering, for instance, A and B here, have very different frequencies, then they are completely negligible, right? Because they happen these terms, these interaction terms are completely off resonant now. And then, of course, if you look further down, like further in the series of the cosine, there's other things that are just very small that we typically also ignore. For instance, where these prefactors go to the order 6 or 8 and so forth, then they become completely irrelevant normally. But all of these terms are in principle there. So what now happens? What happens now when we apply drives to the system? So the interesting thing is now, well, all these drives are again, well, you can think of them as field operators essentially. And if these fields that we induce by driving now in any way are seen by the Josephson junction, then they get mixed in again into all of the interaction terms that we see. Right, okay, the details depend a little bit on your geometry, but all of these photons that we inject into the circuit basically participate now in the dynamics of the Josephson junction and, of course, can now interact with all of the other modes, with all of the resonator modes. And in particular, we have control over the frequencies, of course, of these drives and of these photons that we inject into the system, which means we can make interactions that were previously off-resonant, resonant now. So to be a bit more concrete, we can look at one particular interaction that I want to focus on in particular, and this is swap-like interactions, where we basically create a resonant hybridization between two modes of the circuit. And one way you can think of doing that is by thinking of this problem in terms of four-wave mixing. So which comes in these kind of circuits basically for free, right? Because we have this cosine Hamiltonian, which enables all even orders of mixing between different fields. So the four-wave mixing Hamiltonian that we're considering is basically this. Again, it's a product of two fields, right? Where now each of these photon operators A, B, C, and D can come out either out of the eigenmodes of the system, or could come from these pump photons that we inject into the system. Important distinction is now for the ones that we choose to be pump photons. Those we can basically describe as classical terms, whereas the other ones, of course, stem quantum mechanical mode operators. And well, and as long as we now obey energy conservation, say that in this case, it would mean that the C and D photons, the difference between the Z and D photons has to be the same as these A and B photons. Now this term can become resonant in the whole system. So you see, so what's maybe interesting to note about this is it's really easy to build this, right? Because at the end of the day, as I've shown you in the circuit, so this would be, you can understand this as a transmon coupled to two resonators, for example, and all the ingredients in such a system are already in here, right? So we basically, it's relatively straightforward to build this kind of things because everything comes embedded in any kind of quantum circuit that we'd already make anyway. A little bit of a downside of doing something like this is that it can be a little bit tricky to operate because you can maybe realize that if I multiply these four modes together, there's a lot of potential for what I would call frequency collision. So you might want to say, okay, I want to turn on this interaction between the A and the B mode, right? But I have to be very careful to not create all sorts of other Hamiltonians when I start injecting photons into the system. So to that extent, we don't have to work only with single Josephson junctions, but we can also work with slightly more complicated elements. For example, we can make elements that realize not four-wave mixing, but three-wave mixing terms. So this is basically by combining Josephson junctions in certain ways to set certain boundary conditions that are based on flux quantization in loops. And there we can make completely different things. Like here, for example, this is what's called a snail, a superconducting, a nonlinear asymmetric inductive element. This is, if you tune the flux through this loop correctly, this implements three-wave mixing. And there's some there's a lot of older designs that are a little bit more complex. For instance, this here, a very popular one, the Josephson ring modulator, that's also designed to realize three-wave mixing between three different modes. So there, the Hamiltonian gets a little bit more simple. So here, and the energy conservation requirement gets a little bit more simple. Right here, we only have to have one pump photon, basically bridging the energy difference between two modes that such a system is coupled to, and then we can realize, again, these kind of hybridization, A-Dagger B-type Hamiltonians. The downside of choosing these kind of things is basically that it requires a little bit more design effort to make these things. You can see how this is a bit more complicated to make than, say, this one. Has the benefit that it is a bit less painful to operate because there's much less potential for frequency collisions. Elizabeth, yes. Yep.
So there are a couple of questions about the stuff you're talking about right now. So Jim Eckstein asked if are quasi-particle mixers out of the question because of dissipation?
Well, I mean, I wouldn't say they're out of the question necessarily, but here this is just so this operates purely in a very strictly dispersive limit where we don't have to consider anything than really the modes of the superconducting circuit themselves. So I don't have to even think about, say, properties of the superconductor, besides, of course, the behavior of the Josephson junction. So in that say, I wouldn't say it's more, it's out of the question. I would say from this point of view, I don't have a need of thinking about something like that because from me, that seems to add just a lot more complexity to the story.
Okay. And then Paul asked, in standard nonlinear optics, the interaction is determined by the material and often leads to a polarization dependence. Is that also true here?
Okay, very good question, actually. So, well, I mean, the material here is the Josephson junction, I would say. And the Josephson junction has, of course, a property, has in some sense here a single property, which is really the Josephson energy, basically. And that determines most of what we're doing. And of course, how the different elements are say, coupling to that Josephson. It's like your mode matching, if you like, in nonlinear optics. But other than that, it's a very low dimensional system compared to a real material, right? So polarization, for instance, so like all of this is more or less one dimensional when we built it in superconductors. So in that sense, polarization, for instance, doesn't play a big role. So it's really, I would say, I would not talk about it in terms of polarization. I would talk about like, well, yeah, how do the electromagnetic fields really look like in these systems, and what is the voltage sloshing back and forth through a Josephson junction system, for example. Yeah, it's similar, but I think has a lot less degrees of freedom, if that makes sense.
Makes sense to me. And then one more, do you have an intuitive way of explaining the difference between 4-wave and 3-wave mixing?
In an intuitive way, I mean, okay, there is, so maybe whoever asked that could clarify the question. So yes. Intuitive to me means, right, I mean, I make one photon, I can make 2 photons out of 1 photon by enabling the right interaction, or I need 2 photons out of it. I don't think for me, that's not more to it. Or did you mean on the circuit level?
So Christian, I let you talk if you would like to re-ask your question. But we can't hear you.
Oh, sorry. Oh, no, that's good enough. Thank you.
All right. Okay.
All right. So then let's move on from here. So, okay, so this is like a bit abstractly speaking, how we enable interactions, right? So we blast our system with photons, and due to these photons interacting, generating voltages in the circuit that participate in these Josephson junctions, that can give rise to new Hamiltonian terms. That's basically all I've been saying so far. So now let's see concretely how we can use this in order to make particular interactions between quantum systems. And I'm going to start with what I would call a controlling, routable coherent interactions between different quantum memories. So, and the routing scheme, I said, like, let's look at coherent routing, what I would call that. The idea here is really saying we couple qubits or other kind of elements to a bus system, really, that live, for instance, in a resonator. And what we want to do is enable, play with these couplings such that we can enable pairwise interactions between any two of those, right? So this would be full connectivity. After that, we're going to go to a bit more flexible one, what I would call open system routing, where we really talk about absorbing and emitting propagating photons. So this is an experiment that I want to briefly describe that I'm collaborating on with Mike Hattridge's lab at the University of Pittsburgh. This is ongoing work by his students at the moment. And the idea is that we now have a system that we call the router that has a nonlinearity. In this case, it's a single three-wave mixer. And there are different modes living in that router, waveguide modes in this case. And each of these modes then in turn can hybridize with quantum memory modes, right? So cavities in this case. So all of these cavities, they're high quality, so you could use them as memories. And importantly, what we're going to be doing is we want to enable swap interactions between any pair of those. So I've shown you the swap interaction before, right? We do this by pumping at a given frequency that can bridge the energy difference. So an important design aspect here is that all of the energy differences or the frequency differences between these individual modules are distinct, right? This is what will give us the selectivity in this experiment, right? So that we can selectively go between these guys, for instance. And importantly to note is, this is maybe in contrast to how gates are often done at the moment, is that the hybridization between these systems directly, say 1 and 4 or something like that, is really extremely weak in the system. So if you don't drive the system, there is no interaction, no measurable interaction basically happening between any of those two systems. So how does this look in practice? Okay, so I've shown you the cartoon. This is how it looks in the lab. So what you see here is basically, so the heart piece of this experiment is a waveguide cavity with electromagnetic modes. So these W1 to W4 that I've shown you, they look something like this. So these are simulations of the electromagnetic field in this waveguide. And what you have on the side here are these quantum memory modules. So cavities 1 through 4, right? And what I really like about this is it's extremely modular. As I said, as an experimentalist, this is of great value to me, that we can like swap things out basically. And they're really bolted to the central waveguide, and you can exchange them if you like. And how the individual couplings work, so how these cavities talk to the waveguides in here, and how the frequencies are chosen, is basically all based on geometry, right? So this is basically where these slots for the individual outer modules are. And then what you see around it, so this is basically part of a magnetic shield that isn't bolted on in this case, that then goes around it. And the whole thing, just to give you an idea, is maybe like, like this big, a solid couple of fists, essentially. So this is how the experiment looks like. And what really happens is, so the nonlinearity comes from a single three-wave mixer. So this is this snail circuit that I've shown you. And there's a single one of that here, and this all lives basically here on the side. And due to overlapping fields, hybridizes with these waveguide modes, which then in turn talk to the cavities. So now what happens if we drive the system? So we really have somewhere we have microwave connectors going into the system, and we just apply frequencies at the drives at the right frequency. Now, typical experiment that you can think about then is basically say, well, okay, you turn on these pumps and you try to find the right frequency, and very close to where you had expected it, you can see swapping of excitations between your cavities, right? So this is basically saying you started with an excitation in one of the cavities. I guess this is this right one here. And you monitor two of them, and you see now that they swap, that the excitation swaps back and forth between them. And I can take a line cut here. And what's kind of cool to see here is if you analyze the decay of these swaps, right, is that the fidelity seems, or fidelity in this case, this is done only with coherent states. So there's not no quantum state tomography or anything like that done here. You see that the fidelity seems to be only limited by the intrinsic decay constants of these cavities, right? So we started from like, from no interaction, and by strong driving, we enable these interactions, but these strong drives don't seem to do anything that's detrimental to the experiment. And even though we had basically any interaction in the beginning, we see now that we can swap interactions around in the system relatively quickly. So in the order of up to a microsecond or so for any given pair of cavities in the system. You can play around with that a little bit and really show that this is sort of routable. In particular, you can drive swap interactions simultaneously between different cavities. Now, this is what you can see here. So they don't seem to impact each other in any negative way. And you can also do more interesting things, right? You can enable a swap interaction between this cavity and two other cavities simultaneously. So this is, for instance, something you could use to distribute belt states in this system if you wanted to. Is there a question?
Yeah, there's a question. How are the fidelities affected by the quality factors of the waveguide modes?
Oh, very good question. In this experiment, they're basically not, because the waveguides aren't really resonant with anything. So you can think about virtual, if you want, you can think about that as virtual photons in the waveguide, because it's far off resonant. And the participation in these waveguides is so low that it's really, the decay is basically only set by the intrinsic lifetime of the cavities themselves.
So then the question is the decay intrinsic due to losses in the walls, or is it due to coupling out of the cavity to the transmission line from Jim?
This is a coupling part, actually. In this case, this has to do with how this was measured. And this is also very much related to what Paul is asking. So Paul, and what you're asking, so this is because the measurement is not of population, but in field. This is why you don't, so you would need to square this to get the sinusoidal one. And to Jim's question, the decay intrinsic, yeah, the fact that what's been measured here is the light being, or the microwave photons being emitted from the cavities is a part of the measurement scheme here. It makes it really easy to analyze this experiment. So it's overcoupled in this case. So it's a compromise between measurability and Q factors, basically.
Are you seeing these? So Paul asked to follow up, why does the field not go negative?
Well, it's the absolute.
I see. So this is just the absolute value of the field. Yeah. So, okay.
It's a bit of a quick way of measuring it in this case that gives rise to the way it looks like, but it's a very good question.
And then Simeon had a question too. How do the pump or injected photon frequencies compare to qubit frequencies?
So in this case, so it's a three-wave mixer. So it turns out that the different cavities are all in the order of 6 to 7 gigahertz. No, actually, no, in this experiment, it's a bit wider. So it's, say, anywhere between 5 and 8, for example. That means the pump frequencies themselves are any difference between those. So it's a relatively low frequency. So in the order of 1 to 2 or 3 gigahertz is the pump frequency. So any of the differences, basically.
Thanks a lot.
Yeah, and let me see. Yeah, so this is basically, so this seems to work really reasonably well. As I said, this is all done with coherent states at the moment. So that's why I wrote belt state generation rather than belt state, because it's the point where you would make a belt state. And what the students are currently working on is basically try to really push this into the quantum regime. So add the necessary ingredients to create quantum states in these systems and do actual quantum gate operations in the system. All right, so just as a note, what I've shown earlier here, the system is relatively bulky, and what gets brought up relatively often is basically the problem of like, isn't this very large if you want to scale up? And there's of course ways of making this smaller. So I'm just going to flash an example that was done at Yale, only between 2 elements relatively recently. So where this bus mode is, instead of this really big waveguide, is just a superconducting cable. And of course, in the long run, people have ideas of how to make this all more compact. So this is an idea I worked on myself while I was a postdoc, and people are still working on very hard on this, is, for instance, to integrate all of this into wafer stacks, basically, and not have bulky pieces of aluminum in your quantum computer anymore. I see a question. I actually see it. So someone's asking, how long does a single swap take? It's indeed anywhere between a few hundred nanoseconds to a microsecond. And yes, you can speed it up. In this case, there's always the option of basically driving the system stronger until you see heating effects. This is this. And what you basically, if you want to engineer it such that everything is a little bit faster, it's basically, well, it's the participation of how these pump photons interact with the Josephson junction, right? So how much voltage across the Josephson junction does my field that I'm driving really generate is basically the question. And you can, with clever electrical engineering, of course, you can improve that. So I would say getting a little bit further is possible, but eventually you'll be limited a little bit. Yeah, you might potentially limit your coherence if you go too far in that. So I would say there's room for improvement, but we'll have to see how much room there really is. So I can't really be more concrete than that, I think. All right, moving on. So there are some limitations to this approach, of course, some of them more obvious than others. The most important, some of them are practical. For instance, you can imagine that things get a bit more challenging if you try to attach more and more things to your bus, if you like. Right? And of course, another thing that you have to mention, like everything in this system is relatively high Q, so modularity is not as high as you might maybe want it, right? So everything has to be connected in such a way that you form really good material connections in order for all of this to be very coherent in some sense. These are maybe some practical issues, but one important one, the main important one maybe is the question of addressability. Right, what I've shown you, of course, is that each of the gates that we want to drive corresponds to one distinct frequency difference between 2 of your memories, which of course limits how far you can go, right? All these differences need to stay resolvable basically by a drive frequency. And so this raises all of these, but in particular, this one raises maybe the question of how you can do this even more flexible. And this brings us to the part of, well, can we say, instead of hooking things up such that everything directly hybridizes weakly directly, can we just have different elements of our quantum computer eventually, if you want, talk through propagating photons, right? That we dynamically control emission and absorption, basically, where we can relax some of these requirements. So if some of you have been maybe at my job talk about a year ago or so, then you might have seen already that might have seen some of these things already. But since I'm very excited about it, I'm more than happy to talk about it again. So the idea that we want to pursue here is basically very much inspired by traditional ideas in scaling AMO types of systems, where we really would say we're building cavity QED systems, and we're trying to just send photons between all the different components. Now, the obvious challenge here is that the losses, we would expect, of course, the losses now are much larger in this kind of system. than they would be if everything interacts really nicely, coherently with each other. And it turns out, well, this sounds terrifying in the beginning, but it turns out as long as these modules individually are very good, we can actually tolerate fairly large transmission errors and still end up with a system that shows promise for quantum information processing, right? So in this particular example here, for example, people have shown that you can tolerate errors induced by this photon transmission of up to 10% or so, and still could reach the threshold for fault tolerance in the long run. So there's different approaches of how you can link nodes with propagating photons, of course. The most traditional one in AMO might be how to realize probabilistic entanglement by measurement. Has been done in many different systems, and it has importantly been done in such a way that the rate with which entanglement can be generated in such a network can be larger than the local decoherence rate, which is really what gives this idea some credibility. And these kind of ideas have also been done in superconducting circuits. However, there's an additional way you can take, and this is really highly promising, I would say, in superconducting circuits because the losses there are relatively low. And this is by making use of deterministic emission and absorption of photons, basically. So this is following this seminal work by Sirac and co-workers that have realized basically if you say, well, if you can tunably couple or control the interaction between quantum memories and what we would call communication modes, that allows you to emit and absorb shaped wave packets of photons. And this can be done deterministically, and if there's not a lot of loss happening with arbitrarily high fidelity, essentially. So how would such a system that realizes tunable emission and absorption in a circuit QED system look like? Well, one way of doing this is, again, making use of these mixing ideas, right? In this case, in this architecture that we've used here, right, we use a 4-wave mixer, so a single Josephson junction, to basically create a swap-like interaction between a quantum memory and a low Q cavity, sorry. Right, and by doing this, due to the fact that once photons end up in this low Q element, they leak into a transmission line that allows us to create arbitrarily shaped photon wave packets containing the quantum state that was originally in this cavity here. So what you can do then is by basically, solving the equations of motion of the system and tailor these pump tones here in such a way that you can really make nice time symmetric wave packets, for example. So this is what we've done here. What you see here is like we pre-specify an envelope for this wave packet, and this blue oscillation is basically the wave that we measured coming out of here. And this can be done really, really efficiently and relatively fast compared to the intrinsic decay times of anything in the system. Oh yeah, there's a question.
I think you just answered it, but yeah.
Yeah. Did I answer it, Jim?
Wait, I have to find him if I want to let him talk. All right, Jim, you can talk.
Jim is muted.
Unmute. Am I unmuted now?
Yes, we can hear you.
Okay, so no, I don't think you did, Elizabeth. I'm wondering.
Oh, sorry.
if I think about exciting an atom and the decay rate is, the spontaneous decay time is a microsecond, I don't know whether the photon's going to come off a nanosecond or 10 nanoseconds, 100 nanoseconds, a microsecond, or even beyond that, right? And so you're finding a way here to deterministically transfer the quantum information in your atom here onto a transmission line. I'm just curious, can you tell me why the rules of spontaneous emission, or at least the way I think about that, aren't really controlling the emission of this beautiful wave packet? That's really the question.
So, okay, there's two aspects to that. So what we're controlling is, of course, not the arrival time of the photon, because there you've chosen a basis, basically, right? Like in a click detector kind of picture, that would be probabilistic, right, when it exactly arrives. What we're doing is we're creating a particular wave packet. And in this case, it's not an exponential rise or decay, but it's something else. And we're doing that by basically enabling the decay path for the spontaneous emission is more how you would see it, right? So if your atom, so you can think of it as a dynamically tunable Purcell effect.
Okay, that's what I was kind of wondering. I was wondering if that's what you were doing here. If that's the
exactly
case,
it.
then, yeah, okay, all right.
I'm dynamically modifying the Purcell rate.
Yeah. But you're still, that oscillating wave packet you've got there in the right-hand panel there, or the right-hand figure, that's still one photon, right? Or that's still, that's not, maybe not one photon. It's not a classical coherent wave, right?
We've done it with all sorts of states. I'm not actually sure in this particular plot what I picked here. It might have been a small coherent state or a superposition of 0 and 1 photon. 0 and 1. Basically identical. I mean, it cannot be a Fock state because that doesn't have an expectation value in the field, which is what we're measuring here. So it is something that has that's a superposition of Fock states.
But this is a dynamical control of Purcell control of the emission.
Exactly.
Yeah, you're just opening up the gate and letting it out.
Yeah.
Okay, thanks.
Yeah. And so I think I have to speed up a little bit.
Okay, but there's one more quick question.
Oh, there's a question?
Yeah, so what's the motivation for creating a wave packet of a particular shape?
Okay, so the thing is, you want something that's varying relatively slowly. So the thing is, what you can do, okay, you can say you live with an exponential decay, for instance, but that would have a sharp edge at some point, and that just makes it, in terms of dynamic ranges, very hard to absorb because there's very high dynamic range components in the wave packet now. And technically, okay, what you can show when you look at the math, that would require an infinite amount of energy or dynamic range to absorb or emit a photon wave packet of that shape. So basically what we're saying is, like, we want something that very slowly, consistently, that makes it easy to work with. Purely mathematically, it doesn't matter. So let's see. So then, okay, since we control the emission, we can also control the absorption. These are really the same thing in this system. So you can plug this all together and apply the correct tones. So this is just a snapshot of the actual time profile of the pumps that we're applying here that realize the 4-wave mixing. And you can show that you have done deterministic, you can realize deterministic remote state transfer and entanglement with the system. For example, right, so what you can show is here we've done this with single Fock state superpositions and a full basis of a full qubit basis, if you like. And you can see that you can do this with a mean fidelity approaching around 90% in this case. So this is not too far away from this 10% limit that I've shown you. So we find this generally very encouraging. You can also generate entanglement relatively easily by using the same idea. And instead of releasing everything, you can do this by not releasing everything that was on one side, but only half of it. That basically immediately generates remote entanglement between the two systems. One important aspect is maybe to say that this is, you can do some more things that were in AMO systems not necessarily considered, is that you have the potential of thinking about doing error correction in the system immediately on the transmission itself. And so by basically saying you encode, instead of sending single photons, you send code words. In this case, these are code words of what's called a binomial code. And by transferring those, you can show that you can actually, well, in this case, we weren't able to get an actual improvement. We were only able to basically break even by analyzing this. But by improving all of the systems only a little bit, it would be possible to get additional gains by transferring error correctable states and then correcting for photon loss that happened on the way. All right, with my remaining 3 minutes, I'm gonna, well, just quickly go into the question of what else can we do? How do we make larger or more interesting networks? I'm gonna skip this part. And I'm gonna talk a little bit about an important question of, say, like, how do you now go further? Like, say, okay, we have two systems, but how can you add more? How could you do 3, 4, 5, and how would you do routing in between? And one really interesting idea that has come up in several proposals only this year is basically is the question of how can you realize routing through engineered non-reciprocity? So you can think basically of a full system of many of these kind of qubits basically attached to a single 1D transmission line, if you like. And that would give you everything you want, including full connectivity, if you can control the direction of the emission and the absorption. And a simple way of how you can do that, this is a proposal by Nakamura's group, is basically make use of interference. You can, if you build sort of logical elements here where you have multiple decay paths that can interfere with each other, then you can really have a way of like that the combined wave packet coming out of your module, in this case, it's consisting out of 2 qubits, can either result in a wave packet going only in one direction or the other. And the same holds, of course, for absorption. So this gives you the full routing capability. And the way you do this is, again, this is a talk about mostly about mixing in Josephson junction. You can do this by realizing tunable coupling between, in this case, 2 qubits and their own resonators that then are coupled to a transmission line, right? And they have some sort of relation with each other, right? And if you can modulate those 2 couplings here on the left and the right, that gives you exactly a controllable interference effect here. Between the 2 nodes where these 2 qubit cavity systems connect to the transmission line that allows you to do this. So that was shown very nicely in this paper. And there's some similar ideas by other groups before. And that gives you programmable directionality and routability basically in these systems. And just to finish this, there's some really interesting prospects that you can, for pushing this even further, can realize that when if you have this programmable directionality in these systems, you get some really interesting properties in terms of noise resilience. One thing that you can show is that it becomes possible to become completely insensitive to noise in your communication channels, or if you make more of them and you drive the system in a particular way, that you can engineer dark states in open systems. That become stabilized even in the presence of substantial loss. So there's some really interesting ideas in the direction of autonomous quantum error correction. If you spin this a little bit further, this idea. And with that, I'm out of time, and I'm just going to leave my take-home messages flashed on my last slide. And thank you for your attention and the engagement.
Thanks, Wolfgang, for a fantastic talk. And there was one question that came in at the end, and people should now put in any other questions they might have. So what are the dominant limiting factors for the fidelity and loss in the transfer? And is it sufficient for error correction?
That's a really interesting question. We're still looking into that. So this is something I want to investigate a little closer in the near future. So when you individually analyze all of the parts of the system, it turns out all of them are for practical purposes lossless. So the question is it mode mismatch, which it very well could be. So it might be residual reflections that get kind of masked as loss, but are not actually loss, but just a reflection that directs the photons in the wrong way, basically. This is, I think, my leading hypothesis at the moment, because if you just look at the losses individually of all of the things in the system, they should be like on the single % level or a little bit more maybe, but certainly not more than, certainly not 10, 15%. So this is a really good question. And error correction in the system, you need only about 10% to start thinking about doing successfully error correction. That can be doable. That can be doable, I think.
Thanks. And Paul is curious about your noise insensitivity comment that you blew over there.
That's a very good, that's a really good question. So the way I understand it, so I've talked with some of the theorists that came up with this at some point, and the idea is the limit is that it has to be common mode noise. So it's interference effect at the end of the day. And the important aspect is that you, that the term that generates like the absorption of the noise in the individual nodes is basically ignorable due to interference. That's the important part. And of course, like noise that is only impacting one of the nodes, but not the other, will still result in actual decoherence.
Paul, is that a?
Does that mean that if you if the separation between the two nodes is, I guess you want it to be a lot less than a wavelength? Is that?
No, it doesn't need to be that. So the it needs to you would need to say that you would need to have really good shielding of the waveguide, and the entrance port for the noise, for example, has to be that the entrance port C of the noise, whatever that might be, some imperfection or something like that, is covering the full imperfections for a whole host of nodes, if you like. So that's the important part. Does that make sense?
I have to think about it. So because
your
signal's also coming down and interacting with both of the nodes, right?
Yes,
so I'm having
correct.
trouble seeing what the difference between that and the noise, which also seems common mode in the same way that it's coming down the same.
Yeah, the signal, however, is emitted by this guy in this picture, in this cartoon, emitted by this node and absorbed by this node, whereas the noise comes from somewhere else.
Right. Yeah. Right. Okay. I guess I understand. I understand now. Right. So this is fine as long as you only have two nodes. But if you're trying to make a string of things, then it's less clear how that works then.
Yeah, that's correct. It is. So the detail is in some of these papers. But I think, yeah, the only crucial assumption they're making is basically that you don't start injecting noise here in between the nodes that are supposed to talk to each other.
Got it.
Then you wouldn't be robust against that.
Cool. Thank you.
And there's one more in the Q&A about whether this is good for connecting qubits on the same chip, or if it would be possible to connect across chips.
Well, so the propagating photons on the same chip, that's kind of sort of pointless, I would say. So you would always like favor a coherent hybridization of things because you're already on the same chip. So all it would take you is to connect them with a piece of metal, basically. However, so this is what I'm talking here is clearly off chip. So it follows this picture. I showed one earlier. Let me quickly find it. Like this kind of idea where you have chips in individual housings and you connect them by cable. So this is kind of what this is really made for. So it tackles the next step in scalability if you want. Like you can fit only so much stuff onto a wafer, and especially in microwave wafers, you don't get that much onto wafer as you sometimes would like. And
but you are imagining all in the same dilution refrigerator, I assume, that these are these lines that we're talking about are at low temperature.
Yes, but so if you want to take this fully to the extreme, so I skipped over this slide, but now I finally can flash it. It's an experiment I really like by the group of Andreas Lauraf, only this year. They literally welded two dilution refrigerators together. So this is a shielded 20 millikelvin link between two refrigerators. Oh, there's a typo in here. It's two refrigerators. You can argue, okay, maybe it's just one really big refrigerator because everything is at 20 millikelvin here. But you can play these games of doing this. So this is quite amazing what they've done here. I think the really cool thing would be to find something relaxed in that space where you say maybe, okay, you find a way of connecting things not through 20 millikelvin, but maybe 4 Kelvin, where you wouldn't actually need a lot of this, but maybe only a mildly cooled cable from my point of view. So you only need to go to liquid helium temperatures. And this is exactly where some of these noise resilience ideas come in. This is actually one of the applications here that you might be able to send quantum signal due to this fact that noise can cancel out, that you might be able to connect things through 4 Kelvin transmission lines. So there's a lot of, so if you combine all of these ideas, there might be a lot of really cool things that help a lot in terms of scaling in the future. Yeah, but it's like early stages, and yeah, we're dreaming at the moment.
Excellent. Well, thank you very much for an excellent talk. I think we should wrap up there, though obviously Wolfgang is local, so if people have more questions, I imagine you can get a hold of him. Thanks a lot, and see everyone next week. How do we clap? Paul asks. I have no idea.
All right.
All right. Oh, Paul wants me to clap.
All right, my schedule is empty, my meeting schedule, so I guess I'm leaving this too. All right.